The focus of this unit is on alcohols. As a result of this unit, you will gain a fundamental understanding of what we're referring to when we talk about alcohol molecules, and you will learn how to go about naming alcohol molecules. Alcohols are very important molecules in terms of practical applications. One example is that we recognize compounds such as ethanol and isopropyl alcohol, the molecule shown here, as really effective disinfectants. Alcohols are also very common as intermediates in multi-step chemical syntheses, and we'll often see alcohol functional groups appearing in molecules that are of practical application important, such as a variety of drug molecules as well. So let's go ahead and get started with an introduction to alcohols. When we're talking about alcohol molecules, we will use a classification system to allow us to refer to the type of carbon atom that is bonded to the hydroxy group. And as a reminder, the hydroxy group is the OH group within an alcohol molecule. So when we're talking about an alcohol molecule, we're referring to the situation where we have a carbon directly bonded to a hydroxy group. And keep in mind when we're talking about alcohols that we are not referring to the situation where we have a carbonyl group directly bonded to a hydroxy group. That situation we would refer to instead as a carboxylic acid functional group. So what we're seeing here on the right is definitely a carboxylic acid, not an alcohol. Alcohol has to have the hydroxy group without the carbonyl group next door. So we don't want that carbonyl group in there if the molecule is to be known as an alcohol. We classify these differently. We classify alcohols differently than carboxylic acids because they're going to undergo a very different set of characteristic chemical reactions, which we'll be focusing on later on in this chapter. As we start to think about alcohols and the types of reactions they'll undergo a little bit later on, we need to classify the carbon atom that is bonded to the hydroxy group. And we classify those alcohols as primary alcohols, secondary alcohols, or tertiary alcohols based on the type of carbon that's engaged in the carbon hydroxy bond. So we call it a primary alcohol if the carbon that is bonded to the hydroxy group is bonded to only one other carbon atom. So we'll go ahead and plug in a carbon atom right here, and then these other bonds in black would be going to hydrogen atoms. So this would be referred to as a primary alcohol because there's only one bond between the carbon that has the hydroxy group, shown in green there, and the other carbon of the molecule. Secondary carbon, as you might have guessed, or a secondary alcohol, is going to be an alcohol where we have bonds to two different carbon atoms from our alcohol carbon. So our alcohol carbon, again, is in blue. I'm going to put the two carbons that it's directly bonded to in red, here and here. So that's what would make this referred to as a secondary alcohol because there's two carbons bonded to the alcohol carbon, and then we'll go ahead and put a hydrogen in there to finish off this secondary alcohol. Then finally, a tertiary alcohol, going on up the chain, of course, is going to have three bonds between the alcohol carbon and other carbon atoms. So again, alcohol carbon, that is the one that's bonded to the hydroxy group, is in blue, and our carbon atoms are going to be in red. So we'll fill the complete octet of this blue carbon atom by just putting three other carbon atoms around it. We're going to see that primary, secondary, and tertiary alcohols will have different patterns of chemical reactivity, and so that's one reason why it's important that we are able to recognize and classify what type of alcohol we are dealing with. Now let's take a look at naming alcohols. We'll begin by looking at the IUPAC nomenclature of alcohols. So here's an overview of our guidelines for naming alcohols using the IUPAC system. This should look really familiar to the nomenclature rules that you've seen before. First off, we're going to find the longest carbon chain. And what you have to keep in mind here is that when you're looking for the longest carbon chain, it has to be a carbon chain that includes the carbon that's bonded to the hydroxy group. That is absolutely essential. Much like when you're naming alkenes, you had to find the longest carbon chain that included the alkene group. Here, we're going to put priority on the alcohol group, so you have to find the longest carbon chain that includes the carbon that is part of the alcohol functional group that has that hydroxy group on it. The parent name of the molecule then is going to follow the template alkanol, where the OL portion of the name will indicate to us that the molecule is an alcohol, And the alcan part will be replaced with the specific term to indicate how many carbons are in that longest carbon chain. For example, pentanol would be a 5-carbon chain, hexanol a 6-carbon chain, etc., etc. Then what you'll do is number that longest carbon chain that you found in step 1, beginning at the end closer to the carbon bearing the hydroxy group. So the priority here in terms of deciding how to number the chain is that alcohols are going to take, of the functional groups we talked about so far, the highest priority. So they are going to be the biggest factor in dictating which end of the chain you start numbering from. Secondly, you'll look at the alkenes and alkynes. Thirdly, at alkanes and halides. So in other words, if there's an alcohol group within the molecule, that alcohol group's location is going to determine what end of the chain you want to start numbering from. You'll start numbering from the end closer to the alcohol group. And if there is a tie, then you want to start numbering from the end that will put a branch first, much like what we've done with all of the nomenclature we've looked at in the past. Once you have numbered the longest carbon chain beginning at the end close to the carbon bearing the hydroxy group, you will want to put into your parent name an indication of what carbon number bears the alcohol group. So I'm applying that there as X. So I'm putting X equals the carbon number that has the hydroxy group bonded to it. So for example, 2-hexanol would indicate that the carbon hydroxy bond is at carbon number 2 of the chain there. We'll get different constitutional isomers by moving that group to various points of the chain. Another way to put this, rather than putting it as X-alkanol, such as 2-hexanol, would be to instead specify the molecule as an alcan-X-OL, where X again indicates where the alcohol group is. And by putting that numerical location as close to the alcohol group name OL as possible, that helps avoid any confusion about what we're referring to here. So both of these ways of naming the parent are acceptable based on IUPAC rules from various IUPAC meetings. So then finally, after you have established the parent name and the location of the hydroxy group within that chain, then what you'll do is go back in and totally analogously to what we've done for all of the nomenclature topics we've looked at so far, you're going to go in and name all the branches that are coming off of that longest carbon chain and specify their locations. So this would be where you plug in things like the name isopropyl, the name methyl, the name bromo, etc. at the beginning of the name as a prefix and indicate where it is located. Just as always, separate your numbers from letters using dashes to get the name completely professionally correct. Let's go ahead and use these rules to take a look at naming a couple of example alcohols. So we'll start by taking a look at this example problem where the first thing we want to do is find the longest carbon chain that includes the carbon that has the hydroxy group bonded to it. So longest carbon chain containing the carbon hydroxy group would be this. Then secondly, we want to come up with the numbering for this longest carbon chain. And remember that for that numbering, we want to begin at the end closer to where the hydroxy group is, because the hydroxy group carbon is going to take priority in deciding how to number this chain. So whatever you do, don't start numbering from this end of the chain, even though that would put a branch as close to the end as possible with that bromo branch. That's not going to be right because the alcohol group takes priority when we are talking about naming molecules. So we go to number this. We have 6 carbons in the chain. Our alcohol group is at carbon number 3, so we would call this 3-hexanol. Or alternatively, hexan 3-ol as the parent name for this. Then that parent name, of course, incorporates the fact that we have a hydroxy group here. So I'm going to go ahead and highlight that in, that we've already accounted for that in the name. So all we're left with here then is that bromo substituent right here at carbon 5 that we need to plug in to the name. And we're going to plug that in as our prefix, and it's, like I said, at carbon 5, so we call this 5-bromo-3-hexanol, or 5-bromo-hexan 3-OL. Finally, we need to specify the stereochemistry of this molecule, as we usually do, to finish off our nomenclature of these molecules. So in order to do that, I'm just going to put parentheses here at the front to fill in the stereochemistry. And we have chiral centers at carbons 3 and 5, so I'm going to fill in 3 and 5 for this, and we'll establish the stereochemistry here. So at carbon number 3, ranking the 4 groups that are bonded to our chiral carbon there, which I'm putting a star on. Highest ranked group is going to be the hydroxy group because we have an oxygen directly bonded to our chiral center. Oxygen has a higher atomic number than the other groups. Second highest rank is going to come over this way. Third highest rank is going to be that ethyl group. So going from 1 to 2 to 3 takes us in a clockwise direction, and since the hydrogen is pointed away from us, OH is pointed toward us, that means that we can go ahead and straight away assign this as R because we're going clockwise there with the hydrogen pointed away from us. We come over to carbon number 5, also a chiral center. I'm going to put a red star on that. And we rank those 4 groups that are directly bonded to the chiral carbon. Number 1 going to be bromine because it has the highest atomic number by far. Number 2 coming over this way. Number 3 our methyl group. And number 4, of course, is the unshown hydrogen that's pointed away from us. Since the hydrogen is pointed away from us, we can simply go from 1 to 2 to 3. That is taking us in a counterclockwise direction, so we would describe this chiral center as having the R configuration. So that's 5R, or rather S, my bad. So we're going counterclockwise here, so it's 5S, and as we said before, 3R will give us the full IUPAC name for this molecule. Let's go ahead and do another example problem. In this example problem, we're going to ramp up the intensity a little bit by including both an alkene group and an alcohol group and see how we will go about handling that situation where we have either an alkene group or an alkyne group in combination with an alcohol group. So let's take a look at this example problem. So starting through our rules here, we find the longest carbon chain, and that longest carbon chain, the priority here is to find the longest carbon chain that includes the carbon bonded to the hydroxy group. So that longest carbon chain is going to take us like so through the molecule. And then what we do from there is figure out how we're going to number that longest carbon chain. We're going to start at the end close to the carbon bearing the hydroxy group. So we can just ignore the branches, ignore the alkene group. We want to focus on numbering from the end closer to the hydroxy group. And the hydroxy group, if we number from this left-hand end, is going to end up at carbon number 4, which is a better situation than if we started numbering from the right-hand side, where the hydroxy group would end up at carbon number 5. So we've numbered this properly starting from the left-hand end of the molecule. We have 8 carbons in total, so therefore the parent name needs to have the term oct in it somewhere. And in that name, we will need to specify the fact that we have an alcohol functional group within our parent chain, shown here, at carbon 4. And also within that parent chain that we've traced out, we happen to have an alkene group as well that's encompassed in that parent chain. And so what we will do is design a name that includes both of those terms, the term in the parent name that indicates there's an alcohol and the term that indicates there's an alkene group. So the way that we will do this is we are going to specify how many carbon atoms are in the chain. That was 8, so we're doing oct, and then ene to indicate that the molecule has an alkene functional group, and then dash 4 OL to indicate the alcohol group is at carbon number 4. And to start this, we would need to specify where the alkene group begins. It begins at carbon 5, so we call this 5-octene 4-ol. And so looking at this name, the 5 here refers to the alkene group because that's what's next in line there to specify a functional group. The 4 refers to the alcohol group at carbon number 4. We could alternatively, and just as accurately, instead refer to this as oct 5 ene 4 OL is another perfectly acceptable way to go about referring to this molecule. And the point of putting the numbers closer to the term that indicates the functional group that's there is it's intended to make it easier to look straight away and see that at carbon 5 is where our alkene group starts, at carbon 4 is where our alcohol group starts. So with the parent name that we've specified here, we've incorporated all of the atoms that we've highlighted in the structure in gray and pink. Now all we have left is the remaining methyl group that we haven't accounted for here in green. And so we'll need to plug that in as a prefix at the beginning of the name. So we'll go ahead and do that, and it's carbon number 7. So we call this 7-methyl, and then separating numbers from letters with dashes, dash 5-octene, etc., or 7-methyl, and then that methyl word runs right into the word oct, 5-ene, 4-ol. Finally, we do need to keep in mind the possibility there could be stereocenters in this molecule. So as we look through, is there anywhere we can assign R or S chirality? Based on the particular structure that we have here, we can't assign anything as R or S because we don't have any wedges or dashes. You might be looking at carbon 4 and saying to yourself, hey, that's a chiral center. And you would be absolutely right that carbon 4 is a chiral center, but it's what we call an unspecified chiral center. It's a chiral center where we haven't shown any wedges or dashes, and if we don't show wedges or dashes, the chiral center is undefined. We can't tell whether it is R or S in configuration. And that's a pretty common thing that will happen when one is doing real-world structure determination. Sometimes the experiments required for determining the chirality of a molecule are pretty cumbersome and sometimes nearly impossible to work out the absolute configuration of a chiral center, and so it's left undefined. So we've left that one undefined. On the other hand, though, when we think about stereocenters that could be assigned as E or Z, we have this alkene group here between carbons 5 and 6, and each of the two carbon atoms, carbon number 6 and carbon number 5, have two different groups bonded to them. So carbon 6 has an isopropyl group and a hydrogen, carbon 5 has a hydrogen, and then the chain that has the hydroxy group. So we can assign that, therefore, as E or Z, since we have it spelled out with our accurate trigonal planar shape. So what we do is split this bond in half, look at carbon number 6 and ask ourselves which of those two groups bonded at carbon number 6 is the higher ranking group. It's going to be the isopropyl group, so I'll just put a circle around that. We come over to carbon 5 and ask the same question, which group is higher ranking, the hydrogen that's directly bonded to carbon 5 or the rest of the molecule that has that hydroxy group in it? That's going to be the higher ranking of the two. And so what you'll notice here is that the two higher ranking groups are faced in the same orientation. They're both on the top face of the molecule, is one way we could put that. And so we would define this molecule as having the Z configuration. So this is the Z diastereomer. So I'd plug in the term Z in parentheses there at the beginning and then put a dash to separate that from the numerical location of our first branch. As one last example problem to solidify IUPAC nomenclature of alcohols, what we're going to look at is a cyclic alcohol molecule. In other words, where we have a ring with a hydroxy group branching directly off of that. So for example, something like this. So in the case of molecules that have a ring, what we will do is the ring is going to form the parent name here. So in this case, the three-membered ring. And that hydroxy group branching off of it is going to come into play in the parent name as well. So in this case, a three-membered ring with a hydroxy group is going to have the prefix cyclo to indicate it's a ring. And then 3 carbon atoms is known as prop. So cycloprop enol is going to incorporate all of the atoms that we've highlighted there in green. It's assumed that the alcohol group has to be at carbon number 1 because the alcohol group is what determines priority for numbering chains and for numbering rings. The ring is always going to start the numbering at carbon number 1 when we have either just an alcohol group or a mixture of alcohols, alkenes, alkynes, alkanes, and halides, because alcohols take the highest priority there in determining how we number our chain and also in determining how we number the ring. So the alcohol group will automatically be at carbon number 1 of the ring. And then what you would do here, if there were multiple branches at different locations of the ring, we would number the ring to go in the direction so that we come to a branch as soon as possible. And in this case, our branch, our second branch off of this molecule, other than the hydroxy group, happens to be this isopropyl group, which is right here at carbon number 1 as well. So to specify that, what we do is plug in at the beginning of the name here the term 1-isopropyl, and then run that word right into cyclopropanol. So in this case, since the isopropyl group is at carbon number 1, we put 1 in there. We do have to specify the location, regardless of whether it's carbon 1, carbon 2, etc., because of the fact that that isopropyl group could be at a variety of different spots in the ring. And when it's at different spots in the ring, we would have different constitutional isomers. So we need to definitely use proper nomenclature to identify that. It is also often the case that in addition to using IUPAC nomenclature, alcohols are referred to by their so-called common names. The common names for alcohols are going to be formed by using the terminology or the template alkyl alcohol, where the alkyl refers to the alkyl group that is directly bonded to the hydroxy group. So let's do a few examples to illustrate this. And when we're talking about the alkyl group names here, we're generally referring to those common names that you learned previously, such as isobutyl, neopentyl, tertbutyl, etc. So looking at some example problems of this, a really common compound in medicine cabinets is isopropyl alcohol, commonly used for wound disinfection and things like that. So isopropyl alcohol, the isopropyl group was a group that had a 3-carbon chain, and carbon number 2 was where it connected to the parent chain, which I'll put as a squiggly line here when we're talking about using the term isopropyl IUPAC nomenclature. Here, when we say isopropyl alcohol, what that means is that connected at that branch point is our alcohol group. So we'll plug in our hydroxy group there. So this would be isopropyl alcohol. The IUPAC name for this, so isopropyl alcohol is the common name. The IUPAC name for this, of course, would be 2-propanol, or propan-2-ol. So that would be your IUPAC name is 2-propanol. We could also do such structures, coming up with the common name, as isopentyl alcohol. And for isopentyl alcohol, we want to make sure we have that iso group in there, which is a methyl group at the next to the last carbon of the chain. Since it's isopentyl, that means we need to have 5 carbons in total. 1, 2, 3, 4, 5 we have, and a hydroxy group goes right here. So the isopentyl group is the portion of the molecule that I'm highlighting here in red, and then that connection point to the alcohol is based on where the isopentyl group connects to the rest of the molecules. So that would be our isopentyl alcohol. As one final example of this, we could do something like tertbutyl alcohol, also known as T-butyl alcohol by abbreviating the tert to T. So T-butyl alcohol has our tertbutyl group, that's our tertiary carbon, bonded to our alcohol group right here. So this would be our T-butyl alcohol, the tertbutyl group showing up in pink highlighter there, and then our hydroxy group directly bonded to it. So these are going to be the common names that we can use to describe alcohols. In the next units, we will use these terminology for naming molecules and apply that toward doing a variety of chemical reactions to allow us to synthesize alcohols and reactions that we can do with alcohols once we have synthesized those alcohol molecules. So stay tuned for that.